Hello, my name is Karpowicz, a rising senior of the Mechanical Engineering undergraduate program at Bucknell University. I'm here to present to you the highlights of my summer research work concerning the velocity measurement of fluid flows around an underwater vehicle sailing close to the seabed. This work was done under the supervision of Dr. James Arthur of Bucknell's Mechanical Engineering Department. Underwater vehicles, simply referred to as UVs, are structures designed to move through bodies of water. They have many applications, but some of the more conventional ones fall under the categories of ocean exploration, ocean conservation, and military development. After reviewing over 150 publications on literature pertaining to UVs, it is clear to us that while these vehicles are becoming more and more common, there is still an assortment of issues that need to be addressed regarding their design process. For example, current UVs rely heavily on built-in sensors for navigation as opposed to predictive models. However, many dynamic and predictive models do not account for certain flow conditions, such as those induced by a UV traveling close to a porous seabed. That is, the floor of the ocean, which is typically made of textured sediment and actually has holes. Having well-developed dynamic models enables engineers to more accurately predict how a UV may behave under various circumstances. Furthermore, we hypothesize that the porous surfaces of seabed play a significant role in the dynamic flow patterns around a nearby UV. Thus, the purpose of this research is to determine and characterize the effects that the porous seabed has on the fluid flow around an underwater vehicle. To accomplish this, velocity measurements were taken for a UV model situated on both the simulated porous seabed surface, meaning a surface with holes, and a non-porous surface, meaning a surface without holes. The specific vehicle model used here is a scaled version of the DARPA Suboff, a submarine designed by the US Navy and one commonly used in UV experiments. To simulate the seabed, an array of half spheres with uniform size and spacing was created. The model and various surfaces were then placed in a long, narrow test flume for measurements using a velocity measurement technique called particle image velocimetry. For all test conditions, the water flow rate was fixed at 150 liters per minute. The figures under the results section highlight the three test planes for which measurements were taken. For both test sections 1 and 3, the velocity profiles of the flow are shown. In test section 2, more detailed velocity plots depicting the contours and vectors of the flow are shown for both seabed types. The skin friction coefficient and shear stress, both of which are metrics of resistance, are also shown for each test condition. Some important conclusions can be drawn from these results. First, the presence of the porous media leads to about a 40% increase in the UV's flow resistance. This increase in resistance results in a 12.5% mass deficit and some flow retardation, which can be seen in the velocity profiles for the porous surface in test sections 1 and 3. Overall, these results show that the porous bed effects cannot be ignored in underwater vehicle flow assessments. I would like to thank the Program for Undergraduate Research for funding this project and the Mechanical Engineering Department for contributing their resources and lab space. Thank you for your time and consideration while listening to my presentation.